All right, thank you for coming today. I will be presenting how we got C++ to work inside the Windows and Linux kernel, including the standard library and full exception support. We use this for our open source lightweight hypervisor that leverages C++ 11.14, and it's designed to facilitate hypervisor research. So I'll go into the hypervisor just real quick so there's some background as to why we did this. A lot of people think that hypervisors are specifically meant to virtualize servers or run Windows on a Mac. That's usually the use case most people are familiar with. But there's actually a whole field of research dedicated towards the use of hypervisors when in a lot of cases guest support's not even needed. A good example is reverse engineering. And here are some projects online that we have done in the past, or at least the first one we've done, and then the other three are from various other people. I myself have actually done this 4 times. So using hypervisors like Xen, KVM, and VirtualBox can be extremely painful for doing research with hypervisors, especially when you don't need guest support, specifically because they are so focused on guest virtual machines. So there's a lot of code in there that you don't want. And they also have a lot of legacy support, which also gets in the way of kind of doing your research. So you end up with a lot of people who start writing hypervisors from the ground up to overcome a lot of the limitations with these existing open source projects. And like I said, I've done this a couple times. The first one that I did was in assembly, which was quite the experience. And then I wrote 2 others in C. And so when it came time to having to do this again, I said enough was enough. And I wanted a language that would provide me much better high-level abstractions, but also still provide me raw access to the hardware, because I need that when you're doing something like a hypervisor. So the obvious choice was C++ to do that with. And I wanted to make the hypervisor generic so that I wouldn't have to do this again. So it needed to be able to support type 1, type 2 models. It needed to be able to support multiple operating systems like Linux and Windows and OS X and EFI. So it really had to be this very generic type structure. So the first question that came in my mind, at least when I started the project, was, all right, where do I start? How am I going to do this? Because I need to be able to get C++ to run inside the actual kernel. And especially on operating systems like Linux, that is pretty much strictly prohibited. So what's the starting point? So I took a simple application like this, where it's really doing absolutely nothing, and compiled it. To do this compilation, we can't compile it with the GCC that's sitting on your box, because that compiler is specific towards the machine you're running it on. So whether it's Linux or Cygwin, or if you happen to be using MingW for Windows, there's a lot of stuff in there that is specific to that operating system, so you really do need a cross-compiler. But unlike cross-compilers that you may have used in the past for, say, like developing ARM applications on a different machine, this cross-compiler doesn't actually target an operating system. So you really don't see this happening very often unless you happen to troll the OSDev website very often. But the advantage of using a cross-compiler like this is that when you're done compiling the code, there's really nothing there besides that C++ code that you wanted to compile. What you get when you're done linking in a shared library is what you see here. These are basically the symbols from this very, very simple example. There's really nothing there. So the beauty is that after I'm done compiling this piece of source code with a G++ cross-compiler and linking it as a shared library, and then running readelf, is I now have an elf binary that has some C++ code that I can start working on to try and run inside my kernel. So we're going to need an elf loader. I've got an elf binary, and I've got to somehow run it, so let's build an elf loader. When we're looking at elf, there's 2 different ways that we can view it. We can either view it from the linking point of view or the loading point of view. Unfortunately, if you go to OSDev's website right now and you look up elf loader, you're going to see the linking part, and then the loading part, which is the part that they're supposed to be describing, is totally missing. So hopefully someday we can maybe as a group go in there and clean that up. The linking side is really the part that most of us are most familiar with. When we think of a binary executable, we're always thinking what that .text section that everybody's always talking about, or .data, or .bss. For the purposes of this presentation, there's also .ctors and dtors, and then the EH frame, which I'll get to. And once again, if I take that example and I run readelf on it, I can see all the various different sections that are in my elf binary. So this is all of them that are in this one. There'll be more as we progress this example. It's just kind of useful information to some degree. Some of it, even I, after having done this, have no idea what it is. From the loading point of view, basically all your various different sections need to be loaded into memory. So you can't just take an elf file and copy it into memory and say execute. You actually have to copy it into memory based on what this information is telling you to do, because there are some interesting caveats. So for example, if you look to, we'll go to this slide here. If you look to the far right, there's some alignment information that tells you exactly how the segments will actually get loaded into memory. And so even though this elf file only has a couple kilobytes in it maybe, there's how much memory it's going to take up from a virtual memory perspective is actually several megabytes. And that's because it's going to put the read execute sections at the very top, then it's going to wait until the alignment hits 2 megabytes so that you get good page alignment, and then it's going to put the read write after that. And so you need to pay attention to these instructions and the segments. And the way this kind of works, if we go back to this slide, is like, once again, like I said, if you look at my picture here, all the sections kind of get grouped up into segments. And so what the segments are doing is saying, take these sections and put them here, take these sections, put them there, and now you're ready to run. The only additional thing that's missing is we need to do some relocations. So because we are taking our elf file and putting it randomly somewhere in kernel memory, we have to use position independent code, which requires that we have to actually go through and do relocations. Unfortunately, I don't have enough time in this presentation to go through the intricacies of doing that, but all of our code is online, and you're more than welcome to go there and look at it and tell me all the things I did wrong. But in there is all the relocation code. So we are going to do, in this example, we're going to do a really, really simple one. So now that we have a better understanding of elf, and we have our little example C++ program, we're ready to execute C++ inside the Linux kernel. So what we're going to do is we're going to start by creating a Linux kernel driver. Just go and download your favorite skeleton driver off online somewhere. There's a lot of them. And allocate some read-write execute memory. And for the purposes of this discussion, we're going to ignore the obvious security reasons why you'd never want to do that. Then we're going to copy our C++ executable into memory, that memory we just allocated, and we're going to get the address of that entry function inside the elf binary. Our dynamic symbol table will tell us where that is. That's actually a pretty simple thing to do. And we're going to add the location of the starting address of that memory that we allocated to that entry, because the dynamic symbol table is going to give you the location of that symbol as an offset to the elf binary, because it's position independent code. So it basically says, I've got my binary here, my symbol's located here, but because I located that somewhere in the kernel, I got to know where that first buffer started. So you take that address, you add it to your symbol, and now you've got an address that you can actually execute. So in this example here, I do that very simple math, and I run that function, which, if you recall, just adds 10 to the argument and returns the result. So I should see 20 as my answer. And sure enough, after we got this working properly, that's exactly what we saw. We were able to actually run C++ inside the Linux kernel, which was extremely entertaining. Of course, if it doesn't work, the result's pretty obvious. All right, so that's basically it for the elf loader side of things. Once again, if you have any other questions on how that works, feel free to contact me or ask me questions afterwards. I'll be more than happy to help out. But let's get to the more interesting stuff that's specific to C++. All right, so let's work on making the example a little bit more complicated. Now, actually what's interesting is when we first started this project, just having that much code, we were able to get almost the entire hypervisor up and running, almost. And I'll explain one problem we ran into that required this example right here. But you can actually go and create classes, you can create inheritance, you can do all of that stuff, even Lambda functions, all of that stuff work great by just having nothing more than an elf loader and doing some relocation code. Where we ran into problems to start was global construction destruction. Now, once again, if you go to like the OS Dev website, they'll claim that it's optional. It's not, and I'll explain why. Since we took their word for it, we ran into some problems. So global construction destruction. So have you ever wondered if you create a class and then create an instance of that class globally, how is it that your constructor is getting executed and what happens to the destructor? Well, it just so happens if you write that code, your compiler is going to stick 2 more sections inside your elf binary called the ctors and detors. This is a list of functions that take no arguments and return no result that must be executed. So if you look at the table, it's actually an alignment of 8 bytes because I'm on 64-bit. And so it's literally just a table of functions that you need to run through and execute. So this is where the C Runtime Library comes into play. Your compilers will provide this, and I'll explain some more information on that as we go. But for us, we're going to need to create our own since we don't have an operating system to do this for us. So we're going to create a local init and a local fini function that's going to run through this for us. Now, if you were to take like GCC and look at the libgcc source code, you're going to see a crt stuff.c, which is where this code actually exists. Since we're not using that, like I said, we have to create our own. And the function for it is, once again, really simple. The elf loader provides the struct to the beginning of this function, and all it does is it says, here's the section that has your ctors, go to that section and execute each function in it. And then there's basically the fini function looks identical. And then I'll get to the EH frame stuff later. Also, you might notice that this code is not very C++ core guideline compliant. That's due to the fact that we have a circular dependency at the moment with respect to the C runtime and the libc++, which we actually can remove. And so we hope to do that in the future, in which case we'll be able to port this code so it's a little bit more modern and more compliant. One thing I did find really interesting is, and I know now why, but at the time I did exactly what this guy's doing. When I had this example, I said, okay, well, what would be kind of interesting is why don't I create a bunch of classes that have a whole bunch of different instantiations of constructors and destructors, and I should see this list grow as I add more and more to them. And to my surprise, that was absolutely not the case. The size of that list stayed exactly the same. And instead, what's happening is this function global sub I test.cpp is the function that's actually inside that list. And then that function calls the static initialization and destruction. And this is consistent between GCC and Clang. And so what's actually happening is that as you add more and more instantiations of your global constructors, destructors, the size of that function, that static initialization and destruction function, is what's actually growing. What's really interesting was what was at the bottom of that function. So this takes me back to my example where I had a problem with not being able to completely get the hypervisor up and running, because we did have a couple instances of this example right here, where we had a base class and a derived class, and the derived class had a function. We then had a global instantiation of the derived class. We didn't have global constructor destructor support, but that was okay because we didn't do anything in our constructors and destructors, so it didn't matter. We would take a reference to the globally defined class, or instantiated class rather, and then dereference it, trying to call that function, and we would get a seg fault. I was able to verify that this code is perfectly legit. I'd put it in a normal, Ubuntu as a user space app, went and run it, no problems, but it would always seg fault with a null dereference in our code. until I got global construction destruction working. Not only was the code just easier to work with, but then in addition, this started working without a problem. Come to find out, at the bottom of that fancy function, it's doing relocations for you. So if you think that global construction destruction is optional, you're wrong, because there are certain instances where that function is being leveraged to kind of finish the relocation work. And that was the same for Clang and GCC. Another interesting problem that we ran into was the red zone. So once we fixed that problem, boom, we had the hypervisor up and running. That happened around November, December last year. Didn't really do much, still doesn't do much, but at least at minimum, we were able to get a successful launch, and we all had beers and celebrated. And then I decided, okay, why don't we start and stop the hypervisor over and over and over and kind of stress test this to see if this is going to work. And sure enough, after like 5 or 6 iterations, we would get a seg fault. And then you wouldn't see it for a while, and then you get a seg fault again. So it was very racy. And it was driving me insane. It took forever to try and figure this one out. And so eventually, working with the Linux kernel, it has a really good OOP system, so I was able to actually diagnose this in a sane way thanks to that. I took the address of where we were getting the seg fault, and it was a null dereference, and reverse calculated the location inside the L file where it was actually dying, and was able to attribute the seg fault to the string length function. Now, I had actually written the string length function because at this time we didn't have the standard library, so we didn't have a need for newlib. So we only had a couple functions we needed, so I wrote a custom string length. And being paranoid like I am, I wrote the string length function with a null check. So literally you had this string length function where I checked to make sure that the argument passed to it was not null, and then I would dereference it right after that. And that code where I dereferenced it seg-faulted saying null dereference. How the heck is that possible? I just checked, and it said it wasn't null. So immediately in my head, I'm thinking, well, the only time I've ever seen something like this is I'm getting some sort of corruption from sort of some outside thing. You know what I mean? So like if you're in user space, you'd think multi-threaded problem, right? But I'm not in user space. I don't have multiple threads, but I am in the kernel. And kernels have to deal with interrupts all the time. So immediately after I thought about that, I said, okay, maybe there's an interrupt is firing that's corrupting the stack somehow. So I typed in that into Google, and surprisingly, and then of course I added OS dev, that always helps. And surprisingly, there happened to be an article that talked about the red zone. And a whole bunch of other people who have suffered the same pain I just did. So the red zone is an optimization to System V. So if you're on any system other than Microsoft, you're using System V. And what it does is it basically says if you're a leaf function, so think of it like a tree. A leaf function would be the last function being called in the stack until it starts unraveling. So a string length function is a good example of this because it doesn't call another function, therefore it must be a leaf function. All leaf functions within System V do not need to advance the stack pointer. So it's an optimization that the compiler can put in to save some instructions. And since there's a lot of leaf functions inside your code, that's a pretty decent optimization. The problem is it's not compatible with the kernel, because if an interrupt fires, the interrupt on x86 uses the current existing stack pointer as the location for its stack, and therefore, since you didn't advance the stack pointer inside your code, when an interrupt fires, it starts corrupting the stack for the code that was running there. And so anybody writing kernel code has to turn this off. So if you look at like the Linux kernel flags, this is the first like flag to have in there. Because I'm sure for the same reason, some kernel developer was like, what is going on? So the really annoying part here, though, for me, was that I went to my command line and I looked at my flags that I was passing into GCC to say, okay, please stop compiling with the no red zone by adding this flag. And so then I recompiled all my code, and it still crashed. And I'm like, how is this possible? I know it's got to be the red zone. So a couple hours later, I said, okay, what if I turn the string length function into a non-leaf function? So it's an interesting but very simple test. I basically created a do-nothing function, and I called it from within string length. Therefore, the compiler couldn't assume that it was a leaf function unless it optimized it out, which thankfully it didn't. And therefore, it would have to advance the stack pointers inside a string length. Because it was calling a do-nothing function, that function, its stack can get corrupted all day long because it's not doing anything with the stack, so it just whatever. And I ran that, and sure enough, it stopped crashing on string length. Of course, it started crashing on the next leaf function in the code, and since there's hundreds of thousands of them, well, probably not hundreds of thousands in my example, but there were a lot of them. So, but at least it proved to me that the red zone had to be the problem. So a couple more hours of banging my head across the table, I realized since I'm coding in C++ and I had put the no red zone flag in GCC, I was using the wrong compiler. And I simply just had to change it to G++, and I was good to go. Oops. All right, so I've got a working hypervisor, and now I've got a reliable one. So what about the standard library? I'd really like to be able to do this code up here, like do standard C out and have the output dump out to the serial port. I'd really like to be able to use standard vector. Now, standard vector, no big deal. I can create arrays in C all day long, but a map, well, that's a different story. That's not fun to do yourself, or a hash table, or a lot of other things. So I'd really like to have the standard library. The two biggest ones out there are libc++ and libstandardc++. There's a lot of other ones, more esoteric in nature, but most of them have either been abandoned at this point or they don't support C++11/C++14. And I really wanted to be up to date. And the last thing I want to do is start a project that's already in the past. So those are the only two I get, basically. Since I was using GCC at the time, I said, well, let's stick with GCC. And that was a total nightmare. Lib, standard C++, and sup C++ are very tied to GCC, but more importantly, they're very tied to the operating system of your choice. And they don't like compiling against cross-compilers that don't have the middle of the target defined, right? So I'm doing x86-elf, and normally you would say x86-linux-elf, because I'm missing that center R really gets mad. And there are a lot of other people who have shared my experience. So libc++ it was. It's actually pretty easy to compile to some degree. I'll explain some complications we ran into. Once again, it supports, when I wrote the slides, C++17 wasn't as supported as it is now, so it goes all the way up there. It can be compiled without threading support or exception support, which at the time for us was extremely helpful. Now we support both, sort of. And it works well with both GCC and Clang, which was a must since the time I was using GCC. And it works well with newlib, which was important because I really didn't want to write my own C just to get this in there. There are some disadvantages. To start, there are some functions in libc++ that are kind of stack heavy. And in the kernel, especially in the Linux kernel, which is insane with an 8K stack, some of this stuff can cause a problem. We do have a workaround for it. It's an ugly one, but it works. There is also some annoying things inside the code. For example, I tried to use an unordered map, so I'm all excited. I get to use a hash table inside my code, and I don't have to write it myself. Except when I tried to use it, I found an undefined symbol, and it was because I'm not linking in the math library, since we really shouldn't be using floating point and divide module inside the kernel. So this, the unordered map wouldn't work. And looking at the source code, this is why. If you look at the source code here, they're trying to do some integer division, and normally integer division would round down, and in this particular case, they want it to round up. So first they convert to a float, then they take the result and seal it. Well, there's actually a better way to do this that doesn't require you to do the floating conversions, so I'd really like, hopefully they'll accept a PR for me that changes this, because I'd really like to get this in there. There also is an annoying issue with newlib. Newlib, like GCC, really wants you to define that operating system. So since we don't, it won't spit out a shared library, which leaves me in a very uncomfortable position, because if I am compiling libc++ and libc++ comes with this other library called libc++ ABI, which you also have to have in there, I would end up with potentially duplicate symbols, because if I have a static libc and I'm statically linking those to libc++ for two different libraries, if they share similar symbols, then you get duplicates, and it might work, might not, I don't know. I don't want to try. So the alternative was to compile libc++ ABI as a static library, and take all the static libraries and statically link them to libc++. And that actually works. It's not supported by the libc++ developers, but it does actually work. In the end, the reason why they don't support it is that during the linking phase, it might optimize out symbols that aren't used. And we actually found one of them. It was for exceptions specifically. So we do have to add symbols back if they're optimized out by the compiler. So I'll let y'all talk for future work. We do plan to fix this by implementing our own libc, specifically for libc++. And I think it actually could benefit more than just our project, because I've actually talked about this with several people, and they all share the same pain. Another issue with libc++ was how to compile it. So once again, like I said, it could be compiled, but it wasn't necessarily the most pleasant experience. My colleague and I both actually attempted to do this simultaneously. He tried to get it to work with CMake, and since I like to brute force everything in life, I just basically started hand compiling each source file by hand, and actually got it to work in a couple hours. So I knew it could be compiled. Of course, my colleague's approach was far better, so we continued to work on trying to get CMake to actually work. To do this, you need to use CMake's cross-compilation toolchain, where you basically say what platform you're trying to compile for. And of course, it says you can provide generic or none or something like that, but that never worked. I actually had to say Linux to get it to do what I wanted to. And then you provided some other things. Once the two most important things to notice from this slide is where I'm defining the C compiler and CXX compiler. Everything else is kind of, you can look at it. It's not that big a deal. So when we tried to actually get CMake to do this, when we gave it that cross-compiler, the problem that we ran into was CMake would come back and say, I can't find lib sup C++ or lib standard C++, whatever, the GCC C++ library. Couldn't find it. I'm like, well, I'm a cross-compiler, number one, so I don't have that. Number two, I never compiled it, so of course you can't find it. Why are you even asking for that library? You're being cross-compiled. Well, there's this nasty thing that I learned, and it's like one of those feelings where as you're learning more and more, you're like, oh my God, I can't believe this. So I don't know how many know this, but if you compile a simple Hello World program, normally you're going to give it a -c that tells it to create an object file, and then you're going to take that object file and you're going to give it back to your compiler, and without the -c, it's going to link them all together and spit out a fancy executable. So even if your executable is as simple as that one example I had before, what spits out is going to be pretty big. And the reason why is that just to run that little tiny application, your linker has to go and add a whole bunch of stuff to get it to execute on that operating system. So that includes all your standard libraries like libmath and libc and libc++. There's usually a bunch of header files that the compiler itself is trying to sneak in there. And there's also your C runtime, which are a bunch of static libraries that it's also adding, as well as your libgcc, which has a bunch of other fancy stuff in it. So when you look under the hood as to what the linking phase your compiler is going through, that's what it's doing. All those extra R's is exactly what I just said. So for us, because we're essentially creating our own operating system, really not, but we're playing like that, we have to essentially do this on our own. So once again, I went to OS Dev. I said, okay, what does OS Dev say about this? Well, the first thing they say is you need to create a OS-specific toolchain. And what they do is they say, okay, here's this in GCC, here's this giant string that lists out all the stuff that you just saw in that command line. So when you go to compile, GCC itself has this nasty thing that basically somebody filled in, and what they're telling you is you need to take GCC and patch it with your own set of arguments to that list. I mean, nobody in their right mind would ever do that. First off, why would you want to patch GCC for every version of GCC that you have? I don't want to patch my cross-compiler. And second off, I mean, can you guys read that? Question?
So why does dash no stdlib not work?
Excuse me?
There's a GCC flag no stdlib.
Doesn't work.
Why does it not work?
So, oh, yes, thank you. So the question was, why is it when you ask dash no stdlib, why doesn't that work? I don't know. It just basically ignores your command. I tried, and I would add that flag, and the standard lib would still show up in there. So.
Oh, I'm sorry, one more question. So did you still have references to operator new and operator delete in there somewhere?
So the question was, were the references to operator new and operator delete? In this particular case, we were trying to compile CMake, and it's running through the configuration scripts. So it's basically trying to take your compiler and verify what features are supported and which features aren't. And so I don't have control over that. It's going through a list of, you know, what features can I do and what can I do. And as soon as it can't find a standard library, it pukes all over itself. So another option I have is to manually link everything myself. And that's actually what we had been doing up to this point, right? We had been manually running LD. If you noticed, I wasn't linking with my own compiler. I was linking with LD specifically. The problem with this is that CMake doesn't allow you to do that. They give you these nice two little flags to set which compilers you want, but they don't have the equivalent for LD. And if you go to that link that I just provided, you'll see a whole bunch of people complaining about the same problem. And CMake basically says, well, why on earth would you ever try to link manually? It means you would have to know what all of those crazy args are to get it to work on your platform. So you shouldn't be doing that. You should always link with your compiler. That's the rule, right? And so, you know, that meant that we couldn't do that. So the winning option for us was to create a custom bash script. The custom bash script basically acts just like that giant chunk of string stuff that you saw, right? It takes, if you give it a -c, it takes all your arguments and passes it right off to GCC or G++. If you don't give it a -c, it filters all those arguments just like G++ will, then combines all of the shared objects that we have, or sorry, static libraries that we have and we need, like the C runtime that we just created, and and passes that to LD for you. So it's literally doing the exact same thing that GCC is doing, but it's doing it without a patch to GCC, which is important, right? So this means that I can now use any version of GCC I want, and I can also support Clang. It's a much cleaner solution, and all the dirty hacks that we had to go through to make this environment work are now self-contained in one nice, simple bash script that I can comment. That's really nice and simple to use. So I know it's ugly to script your way out of these problems, but in this particular case, I love this solution. All right, so dynamic cast. At some point, we wanted to try and get dynamic cast working, and I figured dynamic cast was built into C++. It's not. It's part of the standard library. So I learned this one the hard way. If you go back to our original example, when we created that test app, you might have noticed that some of those symbols there are labeled weak, and some are labeled global. So what is a weak variable? Well, if you happen to be compiling in such a way where you've got a whole bunch of, or you've got one symbol that's defined a whole bunch of different times, as long as you have one that's labeled global, then the ELF loader knows when it's doing its relocations and such, the global symbol is the one that it needs to choose. That's the address that it needs to give to everybody else. This is how new and delete work. You can globally define new and delete operators yourself, and that's how this works in your standard, or in the standard libc++ library. Operator new and delete are defined as weak. That way, in your code, you can define them yourself, and since you're not defining them weak, it's going to replace the code for you. What happens if every single symbol that you have is defined weak, and there is no global one? Well, this code here that you see for dynamic cast will fail. In my particular case. In the normal case, no, because I did something wrong. So I figured, well, this code here is from libc++ ABI. So I figured, OK, this code here is failing. That's not my code. Let me go file a bug. So the libc++ developers were extremely patient with me, very helpful. And they basically said, no, that code's been there for a long time. We're pretty sure that works really well. And I'm like, I don't know. I'm seeing this problem, blah, blah, blah. And so he turns around and goes, well, have you taken a look at section blah, dot, blah, blah, blah in the Itanium spec? I'm like, no. And so there's this one-liner in the spec that says, if all weak variables are weak, then you need to pick one, and across all shared libraries, that same address needs to be used across all of them, specifically for this problem. So that way pointer comparison can be used when you're doing things like checking type info. Probably for other reasons too, but that's the reason it bit me. All right, so on to exceptions. This was the really fun part. So we've got a hypervisor, we've got all this crazy stuff working, but in the back of my mind, there's two things that are always haunting me. The first one is the fact that I'm using floating point and division inside the kernel, which I'm sure a kernel developer will want to do very bad things to me for. The second thing is that the STL is designed to use exceptions. Now, I understand you can pass the no exceptions flag and then supposedly exceptions are turned off, but in a lot of cases, yes, they're turned off, but you don't get the error because the API wasn't designed to alternatively give you an error code, so it just fails. It'll call standard terminate and bad things happen. So you're really just putting your head in the sand. If you use this flag, you better know that there's certain things in the STL that are not going to go well for you. Since we're running a hypervisor, I really didn't want that situation, so I said, well, why don't we try and get exception support to work? We've already got C++ in the kernel, why not add exceptions? So let's look at how unwinding works. All right, so if you're writing code traditionally without exception support, the way this normally works is you're going to call a bunch of functions, and when you get down to the bottom, an error might happen. And so what you're supposed to do is return the error, and the person who called you is supposed to check, oh, an error happened. He's going to take that, and he's going to return the error, and the person who called him is going to check that and say, oh, an error happened. He's going to return the error, and eventually it'll get somewhere where it can handle that error, and it'll do something with it. Exceptions are doing the exact same thing for you. They're bubbling that error up, they encapsulate an exception, and then eventually get to a catch block, and it deals with it. Exceptions can be broken up into 3 separate layers. You have layer 1, layer 2, layer 3. The first layer is what everybody is used to. So you say throw, std, runtime error, the answer should have been 42. The second layer is what the compiler is generating. So when you see that throw command, it actually creates these symbols. So if you were to do a disassembly, you would actually see this right here. And you can actually see the spec for this or the code right at that link I provided. Since layer 2 is supposed to be architecture independent, it needs to call to layer 3, which is really defined by the Itanium spec and in part by the system V spec to say this, or basically which ends up calling this unwind raise exception, which goes and does the dirty work of actually unwinding the stack. There are already stack unwinders out there. You have one in libgcc, which I think IncludeOS is using. You have libunwind from Google, and you have libunwind from Apple. It's an unfortunate case where they have the exact same name. So actually, and I believe the libunwind that Apple had was donated to LLVM, so it's there if you want to see it. The problem is they all share something in common, and that is they were all expecting to be run in user space, so they're not necessarily written in a kernel-safe fashion. They're also, they use certain functions that would normally only be exposed in user space. Now, the reality is that someday we want to kind of go in a similar direction, but we were able to write one without the need for that. So our current unwinder that we have right now has no dependencies. It can be compiled without having to link any libraries to it or include any libraries. To do it, we needed 4 different specs: the dwarf spec, the LSB spec, which is for Linux, and really all the LSB spec is doing is adding a couple things to dwarf to support exceptions because dwarf was really meant for debugging, the Itanium spec, and the system V spec. All right, so remember in the very beginning of this presentation, I talked about this EH frame part. So that's where this comes into play. The ELF floater, or your ELF binary, has a section called .eh frame, and your ELF floater is going to, or needs to basically record the location of that, and in our case, it provides it in that same struct. And this function call is providing it to the unwinder, because the unwinder needs to know where are these EH frame sections in each shared library that you have. This section is where all of your unwinding information is located. So if you've ever wondered why, when you turn exceptions on in C++, the executable gets so big, it's because every single function you write needs, in addition to the .text section to describe the actual function in assembly, it also needs an FDE located inside this section that explains how to unravel the stack. So every single function has an additional section in here. So you can imagine how the code would balloon really quick. Now, thankfully at least, these FDEs are compressed. So that's what the dwarf spec does. The dwarf spec basically describes how to compress all the logic necessary to unwind the stack so that those FDEs are at least as small as they can get them. But there are a lot of them in there. What you basically have to do is when an exception is thrown, you're going to be given the instruction pointer of where the exception was thrown. You're going to take that and you're going to go search through that entire list of all the FDEs, and you're going to look for, in this list of FDEs, where is the FDE that describes the function that I'm currently located in. Once you get that, it'll tell you somewhere inside that FDE, or your function, how you need to unwind that stack. When you get to the top of the function in the FDE, what you're going to get is a return address. That return address is the address that would normally be used to return to the function that called you. So you're going to then repeat this process. So you start with an instruction pointer. That instruction pointer basically says, you look up the FDE, you decompress the dwarf code, and that tells you where your return address is. From there, you look up the next FDE with that return address, and that points you somewhere in here, and then you unwind the stack again with the dwarf code, and then you take that return address, you find the next FDE, and you keep doing this. So this is why exceptions can be generally slow, because if you were to not use exceptions, you just return an error code, and there's no searching that has to be done. With exceptions, because it's doing all this work for you, it has to go through a list of all these FDEs, every single function call to find the FDE associated with what needs to happen. Now, there are optimizations for this. For example, normally in newer code, there's actually a hash table that's used, and there are other ways to minimize the size of the table. But in general, the difference is because it's doing all this work for you, it's got to do additional work under the hood to try and figure out how do I backtrack that stack. Now, the next hardest part about this function is just that at some point you have to know when to stop, right? So at some point you got to know, okay, I've searched, when do I actually stop? And the personality function is what's doing that. Now, the personality function is in part provided by the ABI. It's also provided by the compiler, or at least the information that function needs is provided by the compiler. That basically says every single time you get to a certain spot, you ask it, have I found a catch block yet? Have I found a catch block yet? Have I found a catch block yet? And it's actually a little bit more complicated because in addition to catch blocks, it also has to deal with RAII. So what really happens is that sometimes it'll say, no, pretend I found a catch block. And then it will go and handle the destruction of all the RAII objects, and it'll rethrow the exception. So it can continue until it finally does get to a catch block. So that's how it's handling things like GSL finally. And basically, that's exception support. Now, the only unfortunate part about this is if you happen to know the name of the function, it's called phase 2, and that's because you have to do this operation twice, which was also crazy when I first saw it. But there's an explanation on at least the spec as to why. But yes, so not only does it have to do all this work, but every single time you throw an exception, it does the work twice. So that's how I got C++ to work inside the Windows and Linux kernel. Now, with respect to our project, because we are using C++, we are able to better utilize a lot of the newer technologies that are out there. So we actually have a hypervisor now that currently utilizes Travis CI with a complete set of unit tests. We have app-var support for Windows. We leverage coveralls as well as Coverity Scan, Clang Tidy for our compliance, and Google Sanitizers for our dynamic analysis, and the CII best practices. We also use the GSL and the core guidelines. Now, this is an area where I could definitely use some help if anybody here who's better with C++ than I am wants to contribute. This is one area we could definitely do better in. But we do have the GSL in our code base, and we are passing all the Clang Tidy 3.8 checks. Minus reinterpret cast, since I'm in a hypervisor in the kernel, I dare you to find a way to get rid of that. And we do have support for GCC 5.6, C++ 11.14, and Clang 3.8, or sorry, 3.8 and 3.9 should be coming in the next couple of days. I actually have it working on this laptop. So for future work, we do plan to support OS X. We have Linux and Windows right now. We also do plan to support ARM. So that'll be kind of interesting, getting C++ working in the Linux kernel on an ARM device. And I think probably more interesting would be the fact that since we want to support type 1, we would like to be able to get this environment working in UEFI, which means that if I combine it into a script that can statically compile everything, you should be able to generate C++ applications for EFI generically, which would be, I think, an interesting project for people who are doing stuff in UEFI and don't want to be stuck with C. We will be adding extended API support and hyperkernel extensions. So because everything's written in C++, we can extend the hypervisor using inheritance. And since we support shared libraries, that means that I can add more libraries to the code base. So I can actually take the bare minimum hypervisor and leave it in one repo, and then I can create another repo that has the extended APIs and another one that provides guest support. So that allows me to accomplish my overall goal, which is that I want a hypervisor that can work for researchers, that doesn't provide a bunch of stuff that gets in their way. But then if somebody does want to do, say, guest support in the future, we can still support that without cluttering the base hypervisor. So it's a very modular architecture, which is nice. We also do plan to support IncludeOS in the very near future, which I think will be absolutely awesome because that means we'll have a C++ hypervisor and a C++ unikernel. I mean, this is C++. That's awesome. And we also do likely plan to provide a custom libc to get around the new lib issue, which I think will likely be a separate project because I do envision other people benefiting from this. It would basically be a libc specifically geared to support libc++, because libc++ only needs a couple functions out of libc, so I don't need to implement all of it. I just had to do this small subset, which I think other people could benefit from too. Other than that, that's my presentation. Question?
So, in the beginning, one of the comments that you made that C++ toolset didn't really like compiling without flash, right? So, not everything is really problematic. And yet you did a lot of work around Unwind for solving problems with the C library and stuff like that. Usually, the framework for solving this problem is when defining the problem, is when defining the framework, defining the platform. So, in essence, what you did is that you define a target, x86 hypervisor F. And have you considered packaging your work formally as a target for C++ or for Clang, so that the people can use that in just using that target, the hypervisor, and just utilize it.
And so the question was, why didn't I create an OS-specific toolchain for the hypervisor itself? There's a couple answers to that. First off, newlib won't accept any target other than Linux, and I think one other. I think herd is the other one. So even if I created an OS-specific toolchain for the hypervisor to deal with the not needing the bash script, it would not have solved the newlib compiling as a static library. However, being able to get rid of the bash script, sure. If somebody wants to tackle writing that disgusting string thing for us, I'd be more than happy to accept that. Down the road, I also wouldn't mind putting that in there. But I'll be honest, we do have a really big hurdle in front of us, which is that if I was to say pitch something to GCC to say, please accept my patch to your compiler to support this hypervisor, I'd have a whole bunch of Linux developers asking me, why are you putting C++ in the Linux kernel? So at least right now, being a separate project, I don't have to deal with that too much, other than the fact that now that I presented this, there'll probably be a whole bunch of people spamming me. But yeah, that's basically the short answer to that question. Well, it was actually a very good, fair question.
Can you talk about how you're doing compilation on Windows?
Yeah, okay, so that's another good question. So how am I getting this to work on Windows? So Windows uses the MS64 ABI. All of this code is compiled using my cross compiler, which spits out systemv. I don't change that. Now, we do have a user space application in our repo for talking to the hypervisor. That's native C++, and so that compiles in Windows just fine. Right now we support Cygwin, but we will have some support in the near future for Visual Studio to compile both the driver and that user space app. So the question, though, is that all the cross-compiled code that gets loaded into the kernel, how exactly do I execute that in Windows? And the answer is, I have a very slick piece of assembly that does all the ABI conversions, as I call, into my systemv code and back out. And so I actually do all that by hand. That code preserves all the registers, including all of the SSE registers, so I can actually do O3 optimizations inside the hypervisor, which does work. And it handles all those ABI conversions. So that's. I'm running in kernel space, and I'm running, in the Windows case, I'm running Linux applications essentially using systemv inside the Windows kernel. So once again, I don't think they'd be very happy about that either, but it does work. Question?
Yes, sir. Awesome.
Thank you.
With only an 8K stack, typical C++ programming, we try to put a lot of things on the stack so they get automatically cleaned up. Even if they're managed pointers, right? You have to have something on the stack to manage it to make sure they get cleaned up.
Yep.
What has been your experience with writing your C++ code and having to not do that so you don't blow up your stack?
That's a great question. The question is, how did I deal with only having an 8K stack in Linux? So at first, I yelled and screamed for a while because that definitely bit us in the butt. When we were having problems with the hypervisor loading, I built one really big function that printed out the entire VMCS, which is a fancy name for a hypervisor thing. And that would segfault, and I wasted easily 2 days on this problem. Later figuring out that I was corrupting the stack because I was overrunning it like mad. And so basically reduced the size of the function, got rid of the problem until it bit me in the butt again like a week later. So finally I had it and said we got to solve the stack problem. So inside that fancy assembly, I also take a piece of dynamically allocated memory and overwrite the stack pointer. So when I jump into my code, I'm actually running out of my own stack. And then when, yeah, which I know they're not going to be happy about either. And then when we call back to the kernel, I put the stack pointer back in place. Now, one interesting thing is that Linux actually has a flag that if you compile the Linux kernel with, when an interrupt fires, it'll actually check to see if the stack pointer is off in the middle of nowhere. And since we are off in the middle of nowhere, it throws a warning message out on your screen in the form of a kernel oops. It's really a benign error message, but it is detecting the fact that I did that. So yeah, you can't do that. Or at least that's how we solve the problem, but you're really not supposed to do that. So the short answer is, if you don't want to have that ugly hack in there, then you do have to be gentle with the stack inside the kernel, or complain to Linux and tell them to put a realistic kernel or a stack size in there, because 8K is obnoxious.
Have you found that forcing functions to be compiled inline has helped or hurt that? Because I can see it going either way.
Actually, to be honest, I haven't tried that. That's a great question. I don't know. I'll have to give it a shot. Let's go over here. Question. Don't forget your question.
It seems like early on you decided to go down this route of loading an ELF
For a couple of reasons, my colleagues would say, the question was, why didn't I natively get the C++ code to compile into the kernel instead of loading an ELF binary and running it that way? So my colleagues would tell me it's because I have absolutely no idea how to actually work inside the Linux kernel. But the right answer is that I don't know if I could do that in a cross-platform way. So, I mean, I might be able to get Linux to do it. I know people have tried, but getting it to do it also in Windows and also in OS X, which would be even harder. I probably could do it in EFI. Probably could do it in EFI, but OS X and Windows, that would be extremely difficult. So, and then in addition, trying to get the STL on there. So by loading my own modules, not only did it give me a modular architecture, which also was a huge benefit to doing that, but then it gave me a really simple way of handling the cross-platform aspect. Now, there is one big disadvantage to this, and that is that from a researcher's perspective, you look at some of the other projects, they like to call into kernel functions from their code when they're doing research with, like, say, reverse engineering. And because I'm sitting in these modules, you can view the execution of my code as independent. I can't see back into the operating system. Now, the reality is, since I'm running in a hypervisor and in ring -1 a lot of times, you really can't call into the operating system safely because you're at a really high RIQ. But some people like to ignore that. And I'm not going to complain because I clearly like to ignore rules too.
So I know Linus's feelings on C++. Have you been in touch with the Linux kernel community and how they take it?
The question is, have I been in touch with the Linux kernel community and what was their response to our project? The answer is no. I'm pretty sure I know what the response to that question is going to be. Although I did find it surprising. We did advertise. We reached out to the author Phronix, and he was very nice to reblog what we were doing. And there actually was a surprising number of people who were very supportive of our approach, and people who were working the Linux kernel who have all shared similar frustrations with only having access to C. So that part was at least nice. But I mean, come on, honestly, Linus is not going to be happy with what we did here.
One of the reasons that the guys who work in the kernel have traditionally stayed away from C++ is because all the peripheral bits like exception tables, B tables and stuff, that in a kernel mode have to stay non-page memory and you can't have them getting flushed out arbitrarily by the OS. As you say, you usually want to get a high IRQ. How do you manage that? You just load everything to mark it non-pageable?
Correct. We're loading. So the question was, how do I deal with the fact that C++ has a lot of stuff that would potentially get paged out in the kernel? And the answer is yes. We load everything in non-page memory. So it's a hack I've been doing for years. It's not necessarily a great solution to the problem, but it works really well. The issue with it, the reason why you wouldn't do that or don't want to do that is on memory-constrained systems, you have a lot of wired memory because you can't get it back. Question?
Yeah, so I have a very dedicated box with a very specific application. I would love to be able to run it in the kernel. Just with a link to your website, how difficult would it be for me to use this talk and whatever documentation you have and throw this thing into a kernel module and run it in the kernel?
Surprisingly pretty simple. I can show you here. Oh, so the question is, how easy would it be for me to do this on my own if I go to my website and try to use this from here? So if you see here in our entry code, right here, this would normally execute this code, which is our actual hypervisor or the launching point of our hypervisor. But here I can add in any C++ I want, and I can run it, and I can get my result. So that's standard out in the Linux kernel. So the answer is, it is somewhat simple in that aspect. You basically just need to use my existing entry module and a couple others, and then you could start writing your own modules for this. And if you do have any problems, just reach out to me and I'll help you get started. Question?
Why did you have to reference to Itanium specs for 886? I already thought that IA64 was different.
Yeah, you and me both. So the question was, why did I have to use the Itanium spec in so many different instances? And I don't know. Go online and Google it, because there's a lot of other people who have your exact same question. But for whatever reason, stuff that we're using for System V is showing up in Itanium 64 spec for C++. There's actually a lot of Itanium stuff for C++ that shows up. So I have no idea other than the fact that they did it for that architecture. It worked for System V, and so they said, why change it? I don't know. It was mind-blowing to me, too. It was like, I can't believe I need this. I need 4 specs to write an unwinder. I mean, that's ridiculous. Question?
So I know next to nothing about hypervisors, but we do build a lot of baremetal applications on embedded processors. So if you're aware of this, what is the difference between building the tool chain and getting rid of all the standard libraries between a hypervisor and a typical embedded system? What makes this more complicated?
So the question was, what makes getting all this stood up for a hypervisor more complicated than an embedded system? So normally I hope I got your question right, but for an embedded system creating all the cross compilers, normally you're going to specify your operating system type when you do it. Other than that, you're probably going to run into a lot of these exact same problems. In fact, that's like Alfred from IncludeOS has run into a lot of these same problems. And yeah, you're going to have basically the same exact issue. You're going to have to create a cross compiler that can go and compile your code. And then from there, you're going to have some sort of linker that can then get your various different shared libraries linked into your application and executed. So whether you're creating a unikernel or whether you're creating a standalone application for an embedded device, it's the same problem. My best advice is that if you can, use, you're more than welcome to use anything out of our repo. It's all there, and you can statically link it and run all this. But there's also, other projects specific to embedded devices that may help make this a little easier.
The reason I ask is, I'm going out myself here. So in our embedded mechanical keyboards community, we have a lot of code that runs pure C++ that runs on bare metal.
Yeah, there's no operating system. There's no nothing.
But
So
no one uses STL though. So I'm just trying to figure out what is different here.
there isn't. We're instantiating that exact same environment inside the kernel. So you could use what we're using here to make that work. So I would say the steps to do that are basically going to be very similar to that of a unikernel. Because unikernel is exactly the same thing, right? View the unikernel as I've got bare metal. It's really a virtual machine, but I got bare metal that I'm really trying to talk to, and I want to stand up a C++ environment. And so how do I do that? It's the exact same problem. We kind of did the exact same thing here, where we had to try and stand up that C++ environment inside the kernel like it were running in bare metal. So a lot of the stuff that we did here would apply to your problem space. Any more questions? Question?
So why does it need to be a kernel module instead of being a bare metal?
It doesn't. It absolutely doesn't. So what you'll see in the next couple of months is when we go to do this on UEFI, that's exactly what will happen. So we'll stand up this environment and get it to work on UEFI, which is bare metal.
So was that just a bootstrap then?
Excuse me?
The fact that it's a kernel module, is that just a bootstrap just to get it going?
Correct. It's just a bootstrapper to get it going. That's exactly what it is. In fact, actually, my title for this originally was How to Bootstrap C++ in the window, and they said, well, a lot of people aren't going to understand that word, so they changed it to work, which is fine. Any other questions? I really appreciate you guys coming. Thank you.